And currently we are working on query processing, and right after this, we'll be working on query optimization. And query optimization will largely dependent on query processing. So at a very high level, in query processing, we want to go over relational algebraic operations that we learned before, including selection. Yeah, we learned the projection, but not much attention paid to projection because we need to just select the columns, not like rows. So selection, and then we also learned external sorting, essentially sorting records on using the disk because there are too many records to deal with in the main memory. And then we'll be learning 5 different join algorithms, okay? So selection, external sorting, join, and in this case, there will be 5 different join algorithms. And you need to be familiar with each different algorithm. And you also needed to be estimate the running time of each algorithm. And when you are measuring the running time, I mentioned the last time that we need to focus on 2 things. The high level assumption is that the hard drive is the performance bottleneck of the system. And what really matters is the number of block transfers, how many blocks we read or update, and how many disk seeks we are going to do. Like 10 millisecond delay per random disk seek on disk. And whenever we read a block or write a block, there is some cost. So for example, 0.1 millisecond. That's the time cost for each block. And when we are consecutively reading blocks or consecutively updating blocks, because we don't need any disk seek, we are going to maximally utilize the bandwidth of the disk, which is about like 100 megabytes per second, okay? So at a very high level, please understand each algorithm and estimate the running time of each algorithm with a focus on number of block transfers and the number of disk seeks. So that's what we want. And we started with a selection last time. And at a very high level, there are essentially 2 algorithms. One is you read all of the records, the brute force, like trivial, straightforward, or exhaustive algorithm, where you read everything from the beginning to the end. The other thing is when you have a B+tree index built for the search key, then you use it. So at a very high level, there are 2 basic algorithms, and there are varieties of situations that we need to consider. Because the B+tree is an ordered index, we can support such a range queries. So please find all of the records whose attribute A is smaller than or equal to some value V, okay? So this is a typical example of a range query, and whenever there is an index available, then you use this. Otherwise, you read all of the records. And we also talked about conjunctive queries, how to support this. Are we going to use set intersection, or are we going to use just one index to find a set of records and then do some further screening by evaluating some other conditions? These are the kind of things that we covered the last time. And then at a high level, we learned external sorting, and we also studying hash. Well, we studied join algorithms. Okay, so external sort is something very important. So you must have a very clear understanding of this. At a very high level, we have some initial phase, okay, initial run creation, and then you are going to have multiple rounds. Like in the first merge round, you are going to merge like 2 runs into 1 run or 3 runs into 1 run. You are going to merge a certain number of runs into 1 run, okay? And in the next phase, you repeat the same process and you are going to have more and more merge runs until there is only 1 single run created like this, okay? So at a very high level, initial run creation, and then you keep merging multiple runs into a larger run, and you repeat this process, okay? And in more detail, the creation of initial runs is fairly straightforward, okay? You have the main memory, let's just say that is 1 gigabyte in size, and you read all of the record into the buffer, okay? The reserved area in the main memory, like 1 gigabyte. And then you sort the records and you save the sorted records into a file, and that is called the run, okay? So this is the original data that is not sorted. You can see that G, A, D, blah, 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 which is not really sorted. And what we want is we want to sort the records by the first column, okay? And in this example, you can read up to 3 records. As I mentioned last time, very simplified example, but let's assume it. So you can only read 3 records, and then the main memory is full. So you sort the records and save the sorted records into a file, and that is the first run that you have. And then you repeat this process, and as a result, you are going to have multiple initial runs, okay? So this step is fairly straightforward, okay? You read as many records as possible into the main memory, and you repeat this process. Now, once the initial runs are created, then you need to merge them. And the question is, how many runs do you want to merge together? So let's just say M represents the degree. So when M is 2, then you are going to merge 2 runs into 1 run. So in this example, the degree is 2, right? You are doing 2-way merge. 2 runs are merged into 1 run, and another 2 runs are merged into 1 run. But in reality, you may want to configure this degree into something different, like 4, then in this case, you are going to merge all of those four runs into 1 single run. So there's a trade-off between, depending on the degree of merge, okay? So let's just say this degree is increasing, okay? This degree. As you merge more runs into 1 run, then you are going to gain something and you are going to lose something. So everything is really on the number of block transfers and the number of disk seeks. That's what we care about the most. So as we merge more runs into 1 single run, then you can see that when M is 2, then you need 2 merging passes. You start with 4 runs, and in the first merge pass, 2 runs are merged into 1 run. Therefore, you start with 4, and then you are going to have 2. And then after this, starting from 2 runs, you need to merge them into 1 single run. Therefore, you are going to have 2 merge passes. So I'm providing a little more detail today. And what happens is that you can see that each record, like A, having A like this, will be read once and they will be written once during the first merge pass. And in the second merge pass, every record will be read once. And depending on the situation, every record will be written. But in general, we assume that the final run is not written on the disk. That's the assumption that we typically make, okay? The last run is not written on the disk. The reason is at the very high level, as we will probably study today, in general, after the sorting operator, we are going to have some other operator like selection or projection. So what happens is that as soon as this sorting is done and the final run is being created, the run is immediately consumed by the next operator. Okay, so conceptually we are creating this run, but just assume that there's a consumer right after this. So as soon as this record is inserted into this logical run, it'll be processed by the next one. So this thing will be never stored on the disk or not stored on the disk, and then immediately processed in the main memory on the fly. Therefore, we are going to have some saving. Okay. The reason is the main memory is a lot faster, like 10 gigabytes per second. On the other hand, the hard drive at the maximum 100 megabytes per second. So the main memory is at least 100 times faster than the main memory, or even more. So we do some like mechanical optimization, not really fancy algorithmic optimization. We just don't write the last run. So at a very high level, in the first merge pass, each record is read once and then written once. And in the next phase, in the final phase, each record will be read once, but now will be written on the disk. So every record will be accessed 3 times. So if I get back to this issue, how many block transfers are we going to have? In general, in total, each block will be read twice and will be written once. So there will be 3 block transfers per block. So if you have 1 million blocks, so as we will see later, one notation that we use is P sub R, where R is the relation and P is the number of blocks. So in this case, here's a number of blocks in relation R, and there are 3 accesses, okay? 2 reads and 1 write. 1 read, 1 write in the first pass, and 1 read and no write in the final pass, so 3 accesses. So 3 block transfers multiplied by the number of blocks. And as you can see that as M increases, so when M is increasing from 2 to 4, then you will need just 1 merge pass. So 4 runs will be merged into 1 run. Therefore, in this case, you are going to have only 1 block transfer. Every record will be read only once. So things will be changing from 3 to 1, or 3 times B sub R times 2, like D sub R. So at a very high level, the number of block transfers will decrease. Okay, so that's a very important thing. As you merge more runs into 1 run, then you're going to have fewer block transfers, fewer IOs. However, when you gain something, then you may lose something. What I mean is that you may increase you're very likely to increase the number of disk seeks. Okay, simply put, why do we have more disk seeks? When you are merging, when M is 2, when you're merging 2 runs into 1 run, then when you have some memory space, like 1 gigabyte, then you need to partition this buffer space into 3 areas, okay? 1 for each input run and 1 for the last run. So when you're merging 2 runs, 2 input runs into 1 output run, then 2 buffers for the input and 1 buffer for the output. So you are going to use like about 333 megabytes per buffer, okay? 1/3 of 1 gig. So that is when M equals 2. But when M is 4, then you have 1 gigabyte of disk memory, and you are going to have 5 buffers in this case. 4 buffers for input and 1 buffer for output. Therefore, in this case, you are going to have 0.2 gigabyte used for each buffer. And as you use a larger buffer, you are going to reduce the number of disk seeks. So when you move from 2 M equals to M equals 4, then because you will have more buffers, the size of each buffer will decrease. Therefore, the number of disk seeks will increase. Okay, so that's the high level point. There's a configurable parameter. How many runs do we want to merge? Okay, and that will greatly affect the number of block transfers and the number of disk seeks. So if you look at the slide in more detail, there will be lots of formulas that you can see. But as I mentioned last time, please don't be fooled by the complexity of the formulas. The high level ideas are not that complicated. Okay, so one thing is the number of block transfers. And what it means is here is the number of blocks, okay? The number of blocks in relation R, okay? That's a data size, and actually that's essentially the number of blocks. So that is the number of blocks, and this is how many accesses, like per record or per block, okay? You just need to think about how many merge passes you are going to have. And in each merge pass, one read and one write. So typically you're going to have two accesses per record and similarly per block. In the last merge pass, you are going to read only. So this is for read. And why do you have two here? Because there is one read and one write. Okay. So that's why you have two, and that's why you have one. And you're going to see something complicated, but you don't have to worry about all of those. And as I mentioned, if you directly try to use this formula, then you may make a mistake, or the situation that is assumed here may not be relevant to practical situations, or the situation that I describe in the homework assignment or in the final exam. So do not blindly use the formulas. What's happening here is essentially we are interested in knowing the number of merge passes. That's what matters. So when it comes to block transfers, how many merge passes do you have? That's the key question. If you have 5 merge passes, then there will be 4 like previous merge passes and 1 final merge pass. And in each of the 4 merge passes, you have 1 read and 1 write. And in the last merge pass, you have 1 read. So you are going to see that each record will be accessed total of 9 times, because in 4 merge passes, 2 accesses, and in the last merge pass, only 1 access for read. Okay, so 9 merge pass, 9 accesses, and this is essentially the number of blocks. Okay, so you multiply the number of blocks and the number of accesses per block or per record. So is this clear to you at this point? How you can infer the number of block transfers? Would you type Y or no? Okay, thank you, Gabriel. So again, what matters is essentially the number of merge passes. That's what matters when it comes to how many times we are going to read or write blocks. Disk seeks is a little more involved. And what's going on here is this factor, well, this term is related to the fact that as the buffer size increases, you are going to reduce the number of disk seeks. Okay, so let's think about this merge pass. So you are merging 2. Okay, you are merging 2 runs into 1 run. Okay, and let's say that so let's just say that this is 1 gigabyte in size. So it may be a bit misleading because there are 3 records and they're occupying like 1 gigabyte. Yeah, it's probably too much. Or let's just say that they are occupying like 30 megabytes. Okay, how about that? 30 megabytes. And this is another 30 megabytes. So which means that at the very beginning, the main memory that we used for the creation of initial runs was just the 30 megabytes for some reason. Now we want to merge them. And this one is, M here is essentially how big the buffer is. So so let's yeah, so let's actually think about this. So let's just say M is 30 megabytes. Okay, let's just say that M is 30 megabytes. And let's try to understand how many disk seeks we are going to have. So what I mean by that is there are 3 buffers. 2 buffers for input and another buffer for the output purposes. And each buffer is 30 megabytes in size. Okay? So what happens is you need 1 disk seek to fully cover the data here. Okay? So you move to the beginning of this file and you read all of the records occupying 30 megabytes of space on disk. So you just can read the data consecutively while keeping them in the main memory. And when you're at the end, and 30 megabytes in the main memory. So 1 disk seek is needed to fully cover this run. And next, 1 more disk seek is needed to move to the beginning of this file and then keep reading the data. And at some point, you will fully occupy 30 megabytes of this main memory buffer. And then, and also that's the end of this file. So 2 disk seeks will be good enough in that situation. And then what's going to happen is, now you have some records in the first buffer. So let's just say that this is B0 and this is B1, and let's just say this is B prime. So you have 2 input buffers that are full, okay, completely containing all of the records from the input runs. And then there are records, and you have everything in the main memory. So you compare the records. So you have A and B, and A is B for B. So you save this in the output buffer. And then you move on to the next record. So you have B and D, and B is smaller than D. So B is output. So what happens is you have all of the records in buffer B0 and other records in B1, and you compare the records, and then you put the records in sorted order in the output buffer. And at some point, this output buffer will be full. So again, we assume that the output buffer is 30 megabytes in size. So when we are halfway done, then the output buffer will be full. So we save whatever we have in the output buffer in the file. So this is the in memory. So we save them on the disk. And then once they are saved on disk, then we clear this buffer. So this buffer becomes empty. And then we process the rest of the records in the buffers. So what happens is that you will see that there will be 2 disk seeks needed, because total of 60 megabytes of data. And then therefore, when we hit the 30 megabyte boundary in the output buffer, then we save the data on disk. We clear the buffer, clear the output buffer, and then we start filling this empty output buffer with the records from the input buffers. So 30 megabytes saved, and then the next 30 megabytes saved, and then we'll be all set, because the original input data is total of 30 megabytes. So it is what's going to happen when the size of each buffer is 30 megabytes. So we are going to have a total of 4 disk seeks in this case, just to cover this area, okay, in the diagram. And let me change the example, okay? So when M equals 30 megabytes, we have 4 disk seeks. That's what we had. And what if M is 10 megabytes? Then we again have B0, B1, and output buffer B prime. But now buffers are smaller, okay? So what's going to happen is, in this case, and obviously, if we are using the same amount of total memory, then we, in general, will merge more runs into one run. So when each buffer is smaller, then we can introduce more buffers. So obviously, I mean, we can do 6-way merge, but here, just to understand the effect of buffer size, just let's try to merge two, let's try to actually merge like then, let's do a 6-way merge in this case. Probably it's better that way. It's more realistic. Okay, so then let's try to do 6-way merge. Then, or here, let's do like 4-way merge. Yeah, I'm sorry. So change the example, but let's just say now M is 15 megabytes, and we will be doing 4-way merge, okay, 4-way merge. So we have B0, B1, B2, B3, and there are 4 buffers because we are trying to merge 4 runs into one run using the same, almost the same amount of like space, memory space. And we have one output run, which is B prime. So we are again trying to do 4-way merge. So in this case, what's happening is initially we have this run, and again, our assumption is that this is total of 30 megabytes. So using one buffer each, which is 15 megabytes in size, we can fully read the data into the main memory. So we will read about half of the data from run 0. So this is run 0, run 1, run 2, run 3. So in B0, initially, we are going to have half of the data from R0. And P1 will have half of the data from R1. P2 will have half of the data from R2, and so forth. So what you see is we are going to have 2 random disk seeks per input run, because we cannot fully read the data into the main memory. So again, this is 30 megabytes in size. So we first read 15 megabyte of data, and then the buffer is full. So we are going to do some processing, and later on, we will probably process all of the data in the current, in the buffer, like currently in buffer B0. And when we fully process the data, then we are going to empty this, and then we are going to read the next batch of the record from input run R0, okay? So there'll be 2 disk seeks needed. In other words, 1 disk seek to read the first half, and another disk seek to read the second half. So as a result, 2 disk seeks will be needed for each input run. And for the output run, what's going to happen is the output buffer has a size of 15 megabytes. And in total, how much data do you have in total over these like 4 input runs? Each run is 30 megabytes. And then you have 4. So there is a total of 120 megabytes of data. And then you are going to divide this by 15 megabytes, because for every 15 megabyte of data, you need some disk seek. So when this 15 megabyte buffer is full, then you need to save. 1 disk seek is needed. And you need to do this multiple times. How many times? That is 120 megabytes divided by 15 megabytes. And I believe that will give you 8, okay? So here's what is going to happen. But if this is the last merge pass, in this particular example, that is the last merge passes. So you may not need this 8 disk seeks, because the final output run can be consumed immediately by the next operator. So if the last run is saved, then there will be a total of 16 disk seeks. If the last run is consumed immediately without being written on the disk, then there will be a total of 8 disk seeks. Okay, so I'm in the process of working on the homework assignment number 3, and I think you will have some chance to think about those things. So essentially, given the memory, we are going to fully utilize the memory. So how many runs we are going to have, initial runs. So this is more like deterministic, given the situation. However, after you have the number of, the initial runs, then you can make a decision. Yeah, I want to rather like merge 2 runs at a time, or 3 runs at a time, or 10 runs at a time, or I may want to merge all the runs at the same time, okay, onto a single final run. And depending on this decision, you're going to have a different number of block transfers and a different number of disk seeks. And when you incorporate the per operation cost, like per block transfer cost and per disk seek cost, if you incorporate those factors, then you are going to get the total estimated time for this external merge sort. Okay. So do you sort of understand what is going on? Would you please answer using Y or N? So I'm not yet seeing any response from you guys. Okay, thank you, David. Okay, thank you, Ralph. All right, thank you everybody. So for now, I will assume that you guys understand, right? So it is all about how many runs are we going to have initially, and then how many merge passes are we going to have. And then you need to think about how many block transfers and how many disk seeks we will do. And again, there'll be a lot of like complexity in the formula. I personally don't memorize this formula because it's not necessary. And I don't, even if I try to memorize it, I don't think I can retain my memory for a long period of time. I simply cannot do it. So, I mean, everybody's different. You may want to do it like in a different way. That's fine. But my number one recommendation is you first need to understand how each algorithm works. And then at least you need to try to derive the number of block transfers and the number of disk seeks. And that's the core in cost estimation in pretty much every like systems research. So if you are working on some big data system, not necessarily a database system, the time cost, the calculation is essentially very similar to this, okay? So if this is a distributed system, then probably the network is a bottleneck, and how much data are you going to send over the network? That's the key in performance estimation or analysis. And any system that involves hard disk, which is the performance bottleneck, then it is all about the number of block transfers and the number of disk seeks. So it's not really limited to database systems only, pretty much all software systems. And this is a very important argument that you need to make as to among multiple systems, what systems do you need to use? So for example, I have a master's student who contacted me for his master's project, and he wants to compare the performance of like Postgres, Neo4j, and MongoDB. And ultimately, his goal is to come up with some cost like analysis, with a focus on the kinds of things that we discussed today. All right, so I also introduced the join operation last time, and we learned one basic algorithm last time, which is called the nested loop join, and this is a very straightforward implementation of the basic join idea for each record in one relation to a full scan on S. So if you remember, I assume that there are two relations, R and S. And in R, there are three blocks. Okay. In S, there are two blocks. And commonly in each block, there are two records. So it's a way simplified example, but I think we can still do some analysis. At a very high level, for each record in R, you need to do a full scan on S. Okay. So if there are 1 million records in R, and if the size of S is 1 terabyte, then you essentially need to do 1 million times 1 terabyte of reading, like huge amount of reading. Okay. And of course, in general, it would take probably more than an hour to do like to read 1 terabyte of data. But if I try to do this, let's just see, just out of curiosity. So let's just see, like, what is 1 million hours? Do I have 1 million? Yeah, that's probably 1 million hours in years. Yeah, then that is like about 100 years. Okay. If you read 1 terabyte of data 1 million times, then it will take 100 years. So it's going to be highly impractical. Okay. So this is not the kind of algorithm that I would suggest, but this is the like straightforward implementation of the basic join idea. Still, for the purpose of like understanding the material, let's try to estimate the cost. In particular, we want to know why we have those many block transfers and why we have those many disk seeks. So one thing that you can see is each block in R will be read ones. Okay, each block in R will be read ones. So you read this block and then you keep it in the main memory. Okay, each block is about 4 kilobytes in size. So yeah, you can keep it. Okay, and you do a full scan on S, but let's assume that the relation S is relatively big, 1 terabyte of data. You cannot keep everything in the main memory. So you can keep each block from R, I mean, one block at a time in R, but you cannot really keep everything from S. So what happens is each block will be read once. So you read this block for this record, one full scan on S, and you still have this block in the main memory. And for the next record, you do another scan on S. And once you process all of the records in the first block, then you read the next block. And for the first record in the second block, you do a full scan on S. So each block in R will be read once. So you essentially have 1 times BR, block transfers, when it comes to blocks in R, because there is a P sub R blocks in R, and each block will be read only once. However, each block in S will be read many times. The first block in S will be read once for the first record in R, because you do a full scan on S for every record in R. So for this one scan. So the first block will be read once. For the second record, the first block in S will be read again. For the third record, the first block in S will be read again. So what happens is there are those many blocks in S, like 1 million blocks in S, and then each block in S will be read many times. How many times? That is essentially the number of records in R. So you should know that N sub R is going to be a lot larger than B sub R. Okay. This is again the number of blocks in relation R, and this is the number of records in R. And there are way more records in blocks. So, for example, there could be like 100 records, there could be 100 records per block, right? Just think about it. Each block is about like 4 kilobytes in size. And if you have like 100 records in each block, then each record is about like 40 bytes, and which makes sense, right? So you can see that. So at a very high level, why do we have this formula? Yeah, I mean, you can memorize it, but in my own opinion, you don't have to memorize it if you understand this algorithm. Each record, each block in R is read once. So you have 1 times BR. And additionally, each block in S will be read many times. How many times? That is essentially the number of records in R. And then there are those many blocks in S. So the total number of block transfers will be this much. And how many disk seeks are you going to have? So you need to read each block in R once. And in order to read each block, you will need 1 disk seek, because you read it with 1 disk seek and you do a scan, so you will move a lot in the disk, on the disk surface. And then when you move to the next block in R, 1 disk seek is needed. So 1 seek, 1 seek, 1 seek. For every block in R, you need 1 disk seek. And for each record in R, you need to do a full scan on S. And we assume that this relation S is consecutively stored on the disk. Therefore, for this one, you move to the beginning of this relation S, and then you do a full scan consecutively without any additional disk seek. So 1 disk seek is needed for each record in R. So for this one full scan on S requiring 1 disk seek. For the second record, 1 full scan on S with 1 disk seek. So how many disk seek needed? N sub R. So for each disk seek on S, for a full scan, you need a disk seek. Okay, so that's why you have those many disk seeks. And at a very high level, this is too much. And there is an obvious improvement on this straightforward algorithm. So at a very high level, we want to reduce the cost by coming up with a more sophisticated algorithm. So here we have 2 loops, and now we want to have 4 loops. And that will give us the next solution. So we have some complexity in the algorithm for some gain in performance. And it is all about reducing the number of block transfers and disk seeks. So what does it happen? So the problem of the first solution, which is nested loop join, is you do too many scans on S. And again, if I exaggerate, that is like 1 terabyte in size and you are doing too many scans. Like 1 scan on S for each record. And the idea is, let's not do it. Let's do 1 scan on S for each block, not each record. So what happens is, once you read this block, then you don't consider only 1 record. You consider all of the records in the block. And then you try to find all of the matches while you are doing a full scan on S. So it's like you read the first block, 1 scan on S. And when you are doing the scan, okay, when you are doing the scan, you pick the first, you pick 1 block at a time from R, and then what you do is you do a full scan on S while retrieving all of the blocks. And for each combination of blocks, like 1 block from R and 1 block from S, you want to compare, like consider all of the records that are currently in the main memory, and which is super fast, okay? So you consider all of the records in the current block from R and current block from S. That's why you have 2 additional for loops. So at a very high level, you have 2 for loops as before, but not at the record level, but at the block level. and they will give you 2 for loops. And then for each combination of blocks, one from each relation, you are going to consider all possible combinations of records or tuples. So that gives more complexity, but at a very high level, you will do many, many scans on S no matter what. So how many scans do you need to do on S? Previously, for each record, now for each block. That's the difference. So previously you had N sub R, but now you don't have this. You have B sub R because not for every record. This time it is for every block. And you are going to have about like 100 times speed up or even more. Okay. Still, I mean, this will take a long time in general, but this is a great improvement. Okay. And here, previously we had N sub R, but this N sub R is replaced by B sub R. So you are going to get those formulas. So again, previously that was the formulas that we have, but this one will be replaced, these and R will be replaced by B sub R because we do a scan on S, not for every record, but for every block. Okay, so N sub R replaced by P sub R. But again, I think you don't have to memorize this formula. What is important is to understand the high level intuition of nested loop join and block nested loop join. Is this clear up to this point? The things are very, very important. So would you please type Y or N? Okay. Thank you, guys. All right. Then I'm pretty sure you can find more details later on. And the next one is index nested loop join, and I'm not going to cover the cost analysis, but conceptually this is fairly straightforward. So what happens is you have a relation R and you have a relation S. And you have blocks, and in each block you are going to have some records. What's happening is, let's just say you want to do something like this, like R equals R.id is the same as S.id, okay? Let's just say you are doing join between R and S, and the condition is R.id is the same as S.id. And typically, ID is the primary key, and you are going to have a B+ tree constructed for this. So super fast lookup is possible. So here, let's just say the ID is, you are seeing some record, and the ID is 100 and name John. Then you can use this ID 100 to do a very quick lookup on table S using the B+ tree. So you have the tree and you do some search in the tree and you will quickly find the location of the record having 100. So let's just say in relation S, you have like record whose ID is 100. And for some reason, let's just say it has like value 200, meaning something else, I mean, some different attribute value. So the goal is for this record, we want to find all of the matching records from S. And it can be done very quickly using the index constructed, if there is any, okay, for S. So that's the idea of index the nested loop join. You have the for loop, okay? You have the for loop for the outer relation, and there is an index built for the inner relation, so let's use this. Then you don't have to do a scan on S, okay? For each record in R, you don't have to do a scan on S. You use the index and you quickly find it with order of log n complexity. Okay, order of log n complexity. So order of log n complexity. And as I mentioned, when you have a B+ tree, it has really high degree, like 100. So each node will have like 100 of children. So the tree is very, very like the height of the tree is very, very small in general. What it means is that the base is ridiculously big, like 100. Okay, the base is big. So you need like 2 disc 6, 3 disc 6, and the other thing is we do some buffering. So the top, the nodes at the top of the tree are typically buffered in the main memory. So we don't really need to touch the disk for those nodes in the top of the tree. So people trees are going to be actually very, very fast. So for many reasons, things will be working so quickly. All right. So index and nested loop join is one option that we can consider, in particularly when we are doing some join, and you can take advantage of B plus tree that is constructed in advance. And then let's think about merge join. At a very high level, merge join is a fairly good option. Probably it may be the best option when, for some reason, the relations that you want to join are already sorted by the join key. For some reason, they are already sorted. If they are not sorted, then you may want to sort them and then apply merge join. That is another option. But it will be one of the most useful solutions that we are going to use. So typically, we are going to use either a merge join or the next join algorithm that we are going to learn, which is a hash join. One thing that I really want to emphasize here is join is an important problem, and people wanted to optimize this join operation as much as they want or as much as they can, because it is frequently used and it is expensive than many other operations. But it's not easy. So but you can make join easier, and particularly when things are sorted, then it becomes much easier to join. So this is one important principle that I want to emphasize. When you are having a hard data management problem, and think about sorting the data. Because the cost is order of log n. Yeah, this is a little super linear, but log n anyway still is not a very big cost. So n log n is not linear, but it's actually close to linear, which is good. And you will make the problem a lot easier. So sorting is obviously one option that we should seriously consider. And if you are using Postgres, using this explain command, so when you have some SQL description, then if you add explain in front of your SQL statement, then you can actually see the query plan. And oftentimes you are going to see that, oh, Postgres is actually using this merge join algorithm, or sometimes it will use the hash join algorithm, but it will choose between merge join or hash join in general, okay? So let's try to understand this merge join algorithm. It's very intuitive, and it is very analogous to external sorting, okay? It's very similar to external sorting. So when things are sorted and we want to do join, it's just like when you have relations R and S, you want to do the join based on this condition that R.id is the same as S.id. Okay. So one thing that happens is you start from the beginning of each table, or equally their files. So let me call them like files. 2 files R and S, and you want to do like run merge join. So at the very beginning, you have one record from R and another record from S, and they are matching in the sense that they have the same join key value, like their ID values are identical. So they are matching. And then you move on to the next records and they are matching as well. And let's just see the other case. So you have D and C. In this case, C is smaller than D, or C is before D. So in this case, you need to advance the pointer to the next record. So conceptually at a high level, what you need to do is every time near except the like near end situation at the very beginning, you are going to be at one record in each relation. So you have one pointer for relation R and another pointer for relation S, and you compare the join keys of those records, and you advance the pointer that points to a smaller join key value. So when you are pointing one record having D and another record having C, C is before D, or C is smaller than D. In this case, you advance this pointer. Okay, and that is the idea. And when there is a tie, it doesn't matter. You just need to advance one of these two. Okay, so you pick when you have two join keys, key values. I mean, one from from two records, right? Then you pick the smallest value. When there's a tie, it doesn't matter. You just pick one of them, and you advance the corresponding pointer to the next one. Okay, and this case will be a little more complicated when you have duplicates. So what if like A appears multiple times? It may happen that way, and in particular, S had some a composite primary key, which is like ID comma some other attribute X. So for example, one person may have multiple phones, right? Then in this case, ID and phone numbers could form the primary key for this relation S. So what I'm saying is that there might be some situation where like there are multiple occurrences of same key, but it is a matter of extending the algorithm that I mentioned. So at a very high level, you maintain one pointer for each relation, and you are going to advance the pointer that points to a smaller join key value, just like this case. Okay, two pointers, one pointing to a record having D, another pointer pointing to a record having C. Then you have to advance this pointer because it's pointing to a smaller value. Then you will be able to find a match. Okay, so that is the high level idea. One nice thing about merge join is it's awesome. The reason is each record. So let me ask you the question. When you are doing this merge join, in particular when these input tables are already sorted, how many times from the beginning of to the end of this merge join, how many times am I going to read or write this? Am I going to read this this record? This record having A, and 3. How many times am I going to read it? When I'm doing merge join. Please type a number. How many times am I going to read this record having A and 3 when I do merge join? Would you please type a number? You can make guesses. Yes, that's exactly correct. Yeah, so every record will be read only once. And that is awesome. So if there are B sub R like blocks in S in R, and there is a B sub S blocks in S, then what is the total number of block transfers? That is this. And our assumption is we are not going to, so when you are joining these two relations, you are going to have an output relation, but as in the case of external sort, we assume that the output relation is not going to be saved on disk. It'll be immediately consumed in the main memory, okay? So there is no writing. Each record will be read once. So if there are like 100 blocks in relation R, then yeah, how many block transfers are you going to have with regard to R? Yeah, 100 block transfers, because each block will be read only once. Each block in S will be read only once as well. So if 100 blocks in R, 100 blocks in S, then 200 block transfers, that's it. Okay, so it's really, really good. Each record will be read only once. It's like a magic. In theory, it's not going to be any faster than this, typically. Okay. But the downside is that it is applicable when relations are already sorted. Otherwise, yeah, we cannot use it. Okay, it simply doesn't work because the algorithm assumes that each relation is sorted. So time cost, block transfers, very easy. DISC-seq a little more involved, but let's use an example. Let's just say you have 1 terabyte of data in relation R and 1 terabyte in relation S. Okay, and let's just say you are using a 1 gigabyte buffer for relation R and another 1 gigabyte buffer for relation S. Then what happens is you start from the beginning and you keep reading the data, and while keeping them in the main memory, and once you read 1 gigabyte of data, then the buffer will be full. So you have to stop. And then you keep reading the data from the beginning until the next buffer. So there is a buffer for R, and let's just say there is another buffer for S. So when you read the first 1 gigabyte of data, then this buffer will be full. And also when you read 1 gigabyte of data from S and then keep them in the main memory, then this buffer will be full, okay, after reading 1 gigabyte. And then you have one buffer full, you have another buffer full, then you are going to basically compare records from in these two buffers. So you can do the join algorithm. And at some point, so you will process all of the records in buffer R, then you need to read the next batch of records. So what you see is you always start from an empty buffer and you keep loading the data into the buffer. And for each loading, you need one DISC-seq. So how many DISC-seqs do you need for relation R? That is 1 terabyte of data divided by 1 gigabyte, which is the buffer size. And that will give you 1,000. Okay, so 1,000 DISC-seqs will be needed for this relation, and another 1,000 DISC-seqs will be needed for S in this case. And 1,000 DISC-seq means each DISC-seq is like 10 milliseconds. Then what it means is just 10 seconds spent for DISC-seqs. So you can see that, oh, DISC-seqs is negligible. For reading 1 terabyte of data, let's assume that it is more than 1 hour, but let's just say this is 1 hour. So 1 hour for reading the data, okay, without considering the DISC-seqs. And when you consider the DISC-seqs, then there will be additional 10 seconds, which is sort of negligible. So that's the nature of merge join. So this is a fantastic join algorithm, okay, when relations are sorted. However, in general, the relations are not sorted. Then what can we do? So that's the question, okay? That's the question. And that will lead us to this hash join thing. So let's just think about this example. Let me first explain this situation. And probably I may use this slide. Best case scenario. Okay. I'm going to talk about this case. This is a very unusual situation. You have relations R and S, okay? However, this relation S is tiny. Let's just say it is like 1 gigabyte in size, whereas relation R is 1 terabyte. So too big to fit into the main memory, but relation S is very, very small, like 1 gigabyte. And let's just say your main memory is 2 gigabyte in size. Then this is a super trivial case. Okay, this is a super trivial case. You can do things, I mean, this is the like best case scenario, like really fast. What you need to do is you read you read one, you completely read the relation S and then you keep it in the main memory because it's tiny. So one disk C is needed because you need to move to the beginning of relation S and you keep reading this and you keep everything in the main memory. So one disk C, you read 1 gigabyte of data, everything kept in the main memory. Done. And then essentially you have a copy of S in the main memory. And there is some cost, but that's it. So one disk seek and those many block transfers because there is a piece of S blocks and you need to read all of them. So like how much time it will take to read like 100 gigabytes of data? Yeah, it's about like 10 seconds. So one disk seek, 10 millisecond, and completely reading 1 gigabyte of data, the entirety of the of relation S, and that is about 10 seconds. And then you are going to read like all of the records from R, like one at a time, but using buffering. So what happens is, you move to the beginning of relation R after loading S into the main memory, and you keep reading the data from the beginning to the end. And for each record that you read, you don't scan on S, or you actually do a scan on S, but only in the main memory, not on the disk. So you don't touch the disk at all because you just process S in the main memory. And you just need 4 kilobyte of disk memory space to keep each block from R, so it is negligible. So conceptually, one scan on S and you keeping all of the data. So each record in S will be read once. So that's why you have a piece of S block transfers and 1 plus 1 disk seek. And then you move to the beginning of R, so one more disk seek, and then for each record, you do matching. So each record in R will be read only once. And there are those many blocks. So each block will be read once, and there is a piece of R block transfers. So in other words, 2 disk seeks and each record will be read only once. We cannot be faster than this. That's the best case. Okay. So one thing that you should keep in mind is when you are, as a systems architect or as a systems engineer, when you are joining two relations, if one relation is small, then you should fully take advantage of it. Okay. You keep the small, you read the small table only once and then you keep it in the main memory. One disk seek, one read of the entire table. And then one more disk seek for R, and then you keep reading the records and then you do all of the matching in the main memory very, very quickly. So this is the best case. So going back to hash join, the situation is, unfortunately, we are given two relations R and S, and they're too big. R is too big to fit into main memory. Let's just say this is like 1 terabyte in size, and the other one is 100 gigabyte in size, and what you have is only 100 gigabyte main memory. Okay, you have the main memory that is 10 gigabyte, and the size of relation R 1 terabyte, and the size of relation S 100 gigabytes. So 1 terabyte cannot fit into the main memory. 100 gigabyte, which is table S, cannot fit into the main memory. So what should we do? And the idea is partitioning. So at the end of this class, if someone asks me about two important principles of solving big data problems, I may say they're all related to making the problem easier. One idea is to sort the data. Then all of a sudden the challenging problem becomes easier in many cases. The other way is to split the data so that the problem is much easier. Okay, here our idea is we are going to split this. So still we pick a smaller table. Okay, R and S is smaller, so we pick a smaller table and we partition it so that you partition this like S0, S1, S2, S3, S4, blah blah blah, such that each SI, like S0 is small enough to fit into the main memory. S1 is small enough to fit into the main memory. S2 is small enough to fit into the main memory. If you can split the data in S in that way, then it becomes a trivial problem. So it is all about making hard problems into trivial problems. And conceptually, MapReduce, I think many of you guys heard about it, and this is a very like important word. I mean, keyword used in big data analytics. MapReduce is conceptually essentially doing the same thing. You partition the data. Okay. Then how do you partition the data? Well, like what do I mean by well? Here, let's think about this case. So you have two relations. One relation R having columns X and Y, and another relation S having columns X and Z, okay, X and Z. And what we do for partitioning is using the same hashing function for the join key. So again, let's assume that we are joining relations R and S with the condition that R dot X is the same as S dot X. Okay, so we are doing some join like this. And then obviously the join key or the join field or the join attribute is X. So we are going to use the same hashing function like H, okay, applied to the domain X. So in this case, let's assume that we have a hashing function that maps name A or ID A into 0. And let's just say we have another hashing, the same hashing function that is mapping name B or ID B into a hash value of 1. Then what's happening is we use the same hashing function for both relations R and S. So this record having B, so given this record, you focus on this ID or the join key and you apply the hashing function, then you are going to get the hash value 1. Okay, and then you decide to save this record in R1. So why R1? This 1 is coming from the hash value. So in other words, you are using the hash values to split the given table into multiple smaller tables whose indices are essentially the hash values, one of the possible hash values. So R0 will contain all of the records whose hash values are 0. R1 will contain all of the records whose hash values are 1, including this record. And similarly, when we apply the same hashing function, when we are considering the records in S, all of the records whose hash values are 0 will correspond to S0. And all of the records whose hash values are 1 will be assigned to S1. So what you see is that all of the records commonly having A will fall into R0 if they are in relation R, or S0 if they are in relation S. So having A means hash value of 0, so it's either R0 or S0. So what you see is that when you use the same hashing function to both input tables, then what happens is you just need to join R0 and S0, R1, S1, and R2, S2. You never, ever need to join R0 with S1 because it is guaranteed to be an empty set. Okay, it is guaranteed to be empty set. So if records having A are assigned to R0, then in all records having A in relation S will fall into RS0. It will never fall into S1. Therefore, matching records must have same indices. Okay. So you just need to do join of R0, S0, R1, S1, R2, S2. So that's the key idea of hash join. Okay, so does that make sense to you guys? At a very high level, join is a hard problem. However, it's super easy when only one of the tables is small enough to fit into a main memory. Okay, why join is hard? Because we want to do it as fast as possible. But when the smaller tables is small enough to fit into a main memory, then just read the small table and load this into the main memory. And then the problem almost solved. So in general cases, how do we do this? You pick a smaller table given 2, and then you split the smaller table so that each small pieces after partitioning will be small enough to fit into the main memory. And you apply the same technique to the other relation R, and you do matchmaking a lot easier because now there is a guarantee that you're going to have many pairs, but in each pair, one smaller table will be small enough to fit into the main memory. Okay, so I think at a very high level, what it means is that every record like A, this record will be read once and then will be saved once. And here, this record having A will be read once and then saved once. And then each record will be read again when you are joining R0 with S0. So you can see that every record will be accessed 3 times. Okay, one read during partitioning, one write during partitioning, and one additional read during, we call it probing or matchmaking. Okay, people call it like probing. During the probing phase, one more read. So when there are B sub R